All right, so I was gonna go over the final review here. Uh, if you pull out your final exam preparation packet, I'm just gonna run through the numbers on that sheet. Um, I'll try to link to the chapters for the homework if you want to look back over those. If not, no big deal, but I'll try to link those up for you. Starting off with number one, basic definitions, I want to highlight with population sample parameter statistic, be able to identify any of the four of those in one problem. So I could give you one problem that gives you the population, the sample, and a parameter and a statistic from them. And I'm looking for you to be able to identify, what's the population, what's the sample, what's the parameter, what's the statistic. So an example of that would be saying I'm interested in um, finding out what percentage of all TW students are taller than 6 foot. I take a sample of 55 students and find that 10 of them are taller than 6 foot. So in that problem, I've given you a population, a sample, a parameter, and a statistic. The population is all TW students, and the sample is the 55 that I selected. Notice that I'm adding the adjective TW students because that applies to everyone in the population sample, but I'm not adding anything about who was taller than 6 foot because that's a variable. That is part of the what. That goes with a parameter statistic. The population sample is the who, a parameter, and the statistic is the what. So it's the idea that the parameter would be the percentage of all TW students who are greater than 6 foot, and the statistic would be the percentage of the sample. So 10 out of 55 of the randomly sampled TW students that are taller than 6 foot, that'd be the statistic. So be able to separate those. Qualitative, quantitative, discrete, continuous, just be able to identify those as examples. It's been a long time since we talked about those, but remember that all data is either quantitative or qualitative, can't be neither, can't be both. Qualitative data is names or labels, words, or numbers that are used for naming and labeling, numbers that are not actually useful. You can't actually do math with them. Things like names on a jersey, colors of Skittles. That would be qualitative. Numbers like phone numbers and zip codes. You could average them, but the result wouldn't mean anything. Wouldn't be actually useful. Quantitative data is numbers that you can do math with. You can average them, and it makes sense. You can subtract them, and it makes sense. When all quantitative data is broken into discrete or continuous, again, can't be neither, can't be both. Discrete data has gaps, continuous doesn't. Explanatory response variables, make sure you can identify those, either if it's in a simple problem like here's a scenario, identify what's the explanatory, what's the response, but also it's important to be able to identify that within the problem because within the context of a correlation and regression problem, a lot of times we'll say something like, for instance, we don't interpret the y-intercept if it doesn't make sense that x is 0. Well, you have to be able to identify which of the variables is x because y can be 0 or not, and that doesn't matter at all. What matters is, does it make sense that x is 0? And so we need to be able to identify which ones which. Remember, explanatory is the x, the response is y. And then our notation, just make sure you go back and know our symbols, know how we can write things when we say that a variable follows a certain distribution in symbol form. Things that you've seen, just make sure you go back and look back over those because it's been a while. The last few weeks we dived into hypothesis testing and correlation regression. We had very different notation there than we had previously, so just make sure you brush up on that so that you're not confused at any of the notation that you were to see in the final exam. Number two, describe the shape of a distribution. Remember that right skewed, left skewed. Right skewed means it has a longer right tail, left skewed, a longer left tail. And symmetry, it doesn't have to be perfectly symmetric as long as it's roughly symmetric. We'll say that's symmetric. Roughly the same thing happening on the left as the right. Doesn't have to be exactly perfect though, if we're just identifying between symmetry and skewness. And then the mean and the median of a distribution. Remember that the mean is not robust. It's not resistant to outliers or skewness. We can kind of think of outliers and skewness as similar in their effects and what's going to happen. They're not the same, but they are very closely related. And so the mean is what's going to be affected by the outliers and by any skewness. And so if we're identifying them on a plot, we would say that the mean is the one that's pulled further to the skewness. Okay, it's pulled further out towards the tails. The mode is the peak of the distribution, right? Because the y-axis of one of those plots is frequency. Mode is the observation that occurs with the greatest frequency. So mode's the peak. The mean is the one that's pulled furthest away towards the skewness, towards the outliers, and the median would be in between them. And again, that's why when we talk about what measure of center is appropriate to use when we have skewness or outliers, we say it's the median and not the mean, because the median is more reflective of the center. The mean is going to get pulled further away and maybe not be as representative. Number 3, give it a set of scores, find the mean and the median, add standard deviation and variance to that. As you've seen throughout the course, we kind of build this up for an in-person exam. So we talked about the whole do without a calculator type thing. Obviously in your exams, you have full use of Excel and a calculator. And with that comes being asked about standard deviation or variance on this exam is on the table. Do note, however, it'll be a small distribution, a small data set. It won't be 50 observations or something like that, because it'd be really tedious. You have to make sure you typed it all in correctly. So I don't want to stress you out with that. If you're asked to find the mean, the median, the standard deviation, or the variance, it'll be a relatively small data set. So whether you have to do it by hand, a graphing calculator, Excel, it doesn't matter. However, you have to get that. And related to that, be able to go back and forth between standard deviation and variance, right? If I have standard deviation of 9, what's the variance? That's something that we should know relatively quickly off the top of our heads. If I have a standard deviation of 9, to get to the variance, I square it, so it's 81. If I have a variance, I square root it to get the standard deviation. So be able to do that relatively quickly and simply, and either in just a quick problem, right? It could just be that's the whole problem, but it may be embedded in a problem. They give you standard deviation or variance, and you actually want the other one. You may be given the formula for standard deviation or variance, may ask for the other one, right? And I may give you the formula for exactly what I'm asking for. Just be on your toes and be able to say, I can work with whatever formula I'm given, and if I need to go back and forth between standard deviation and variance, I can either square or square root. I can feel comfortable with that. That's where you want to be. Know what unit of measurement, mean, standard deviation, variance, and z-scores have in an effort to avoid a really long exam. We may avoid a question that says find the standard deviation, find the variance, find the z-score. We may say instead, if you were to find it, what unit of measurement would it have, right? Remember that the unit of measurement for the mean, the standard deviation, the median, and the mode as well would all be in the same units as the original data set has. So if the initial data set is in gallons, then the standard deviation and the mean are both in gallons. Variance would be in gallons squared. And then z-scores are unitless. They have no unit of measurement. And that's why they're helpful. And that's how we know to use them one way, is when we are trying to compare two things from populations that are dissimilar. That can be because of units. It can be because they're just dissimilar populations. So one example would be, I wanted to compare how I did on the ACT versus the SAT. The units aren't the same. And so by converting to z-scores, now I've put them on the same playing field. Or another scenario is maybe the units are the same, but the two populations are different. It's two different genders, two different age ranges, two different, whatever it may be, two different experience levels. And I would say it's not really fair to compare these two things just as a raw score. So what do? I convert them to a z-score. I standardize them. That's one of the terms earlier, right? Standardized value. We standardize them by taking a value, subtracting its mean, divide by its standard deviation, and now we can compare the z-scores. So be able to do that as well. Number 4, know the properties of binomial, the z and the t. The binomial we've talked a lot about throughout the course, how to identify if something's binomial, right? It's those 4 characteristics. Fixed number of trials. Trials are independent. You only have 2 options, and those 2 options cannot happen at the same time. And the last was that the probability of success is constant. Make sure we catch that. A lot of people struggled with that idea. It doesn't matter what the probability of success is. What matters is that it's constant. Okay, it doesn't matter if it's high, if it's low, if it's weird, if it's what you expect or not. It matters that it's constant. So ask yourself the question, is the probability of success the same on the first trial as the last trial, as all the trials in between? And if the answer is yes, no matter what you think that probability is, if it's what you expect or not, as long as it's constant, that's fine. That's binomial, or it's one of the 4 pieces to be binomial. If you say there's some reason for me to think that the probability of success is different on trial 1 versus trial n, then that makes it not binomial. And then the z and the t, we've talked a lot about those. You've seen those questions a lot. The z distribution is synonymous with standard normal. Remember that adjective standard takes normal, which is just bell-shaped curve, and converts it specifically to the z distribution. There's one of them. That's the normal distribution with a mean of 0 and a standard deviation of 1. T distribution, there's an infinite number of them. right? They all are bell-shaped curves. They all are normal. They all are centered at 0, but their standard deviation is larger than 1. Bullet point number 5, that maps to chapter 4. So 5A maps to chapter 4A's homework. 5B maps to chapter 4B's homework. Really encourage you to go back and look over those. Students oftentimes struggle with this because it's been a long while since you've thought through this probably. This is the reaction I usually get to this is, I completely forgot we did this. So remember in these scenarios that we're often dealing with either a table that's x f of x, or we're dealing with a binomial scenario and we can find f of x via the formula. Remember, in a discrete scenario, f of x is a probability. So how I work through these probability questions is very different for the work that we did in chapter 4 for discrete variables than the work that we do otherwise with continuous variables. My goal here is to rewrite the probabilities as the summation of a bunch of probability x equals something. Right, so I would take probability x less than or equal to 2, and I'd rewrite that and say that's the probability x equals 2 plus the probability x equals 1 plus the probability x equals 0. So I work through those discrete problems. And then probability x equals 2 is f of 2. Probability x equals 1 is f of 1. Probability x equals 0 is f of 0. Remember, that doesn't work in continuous. Right, in continuous, we don't deal with probability x equals, because in a continuous distribution, the probability x equals something is always 0. There is no probability for that. Okay, but in this case, we can, in discrete, that does matter. We convert it to f of whatever the number is, f of x, and then we go to a table or we go to the binomial probability in order to plug in and continue working. So be able to work with those probability questions. Again, probably been a long time since you thought about them, so highlight that, go back and look at those. Additionally, be able to find expected values, standard deviation variances. You'll be given all the formulas. The same formula sheet that you use for exam 3 will work for the final. But be able to go back and practice those. Go back and look at some of those homework problems if you need extra examples. There's the supplemental notes. There's also the textbook. You can go to chapter 4 and find some extra problems there. Bullet point number 6, 6A tracks to chapter 6B, 6B tracks to chapter 6B, 6C kind of tracks to everything. It's kind of underlying throughout all of chapter 6 and 7. Then 6D tracks to 7A and 6E tracks to 7B. If you can do the chapter 7 work, you can do the chapter 6 work. The difference is in chapter 6, we're talking about one individual value. What's the probability that one person's weight exceeds something or is less than something? Whereas when we get to chapter 7, we're talking about what's the probability the average weight of a group of people. So it's the difference between an X and an X bar problem. Be careful when you work through those. Answer what the question's asking you. If you're given X, answer the question for X. If you're given X bar, answer the question for X bar. Just because you're given some extra information may be helpful, maybe not. Just pay attention, follow through with what the question's asking you to do. That's my biggest advice there. And on this one specifically, I would highlight 6E. Again, that's that 7B work. That's oftentimes missed. Those probabilities involving a sample proportion questions. Those are oftentimes a little bit more difficult to work with, and so I'd encourage you to go look back over that material. Remember there, because we are working towards a z distribution, then our goal is to convert the probability statements to probability z less than. If you have a greater than, we use the 1 minus trick. If you have in between, right, we convert to probabilities and then subtract. So remember your tricks for that, but we want to get to that probability z less than, because that's what allows us to go to our z table or Excel, because both the z table and Excel will work with less than probabilities. Okay. Bullet point number 7 is chapter 8. Remember, confidence intervals, a point estimate plus and minus a margin of error. Be able to assess the claims. That's one of the things I want to call out here. Remember that the confidence interval is the set of all values that I think the parameter could take. And so I like to look at it and say, oh, well, then the parameter could be this, it could be this, it could be this. And just say that to myself 5, 6, 10 times, whatever it may be. And then assess the claim. The claim says, the truth is greater than 15. Okay, well, did all the numbers I say, were they all greater than 15 or not? If they were, you say yes, the entire interval agrees with the claim. If they weren't, then you say no, the entire interval doesn't agree with the claim. Okay, so kind of just play that what if game to walk through all the possible values in the confidence interval and say, does the entire interval agree? If it does, again, you can conclude the claim. If it does not, you cannot conclude the claim. Remember, with confidence intervals and hypothesis testing both, we always need a parameter word. We're always making an inference on the parameter. That's one of the key concepts that I need to make sure you understand leaving this course, is that we work on a sample. That's where we get the data from. That's where we do the work, so we do the calculations, but then the end inference is always on the population. Okay, so our conclusion, whether it's a confidence interval or hypothesis test, always needs to have some population word, all real, known, true, actual, population, right? Population is a population word. So lots of options there as to what word could be used, but we always want to make sure we're making an inference on the population. The sample is what we use to get the numbers, but then we're going to take that and the final conclusion is some inference about a population. So we always want to include a population word. So don't forget that. And so when we get to bullet points 8 and 9, hypothesis testing and correlation and regression, I'm not going to spend as much time there. We've covered those recently. Hypothesis testing, of course, chapter 9, correlation and regression is our last chapter that we covered. That's chapter 12. And make sure, though, that these couple of key points that I'm going to go over, these are the things that were kind of more missed on the last exam. So I want to kind of make sure that we're all on the same page here with these. Remember that what symbols can go in hypotheses? It's parameters. Parameters can go in hypotheses. Statistics cannot. So the question, what can go in hypotheses, is just another way of me asking you, do you know what your parameters are? Remember, if you know your symbols and you start off with the word population, that's a parameter. If you start off with the word sample, that's a statistic. Can't go in hypotheses. Know some definitions, p-value, power, type 1, type 2 error, things like that. When we talk about a p-value, again, we use the sign in the alternative is going to be the sign in the probability statement for the p-value, with the exception of a two-tailed test. A two-tailed test is multiplied by 2, and we use the sign of the test statistic to tell us which direction to go. We don't put up not equal to. We say if we have a positive test statistic, we use greater than or equal to. If we have a negative test statistic, we go less than or equal to. Power, type 1, type 2 all have 2 pieces. What did you decide and what was the truth? You can't just give one piece, right? So a type 1 error is rejecting the null, but the null was true. So you can't say type 1 error is just rejecting the null, and you can't just say the null is true. It has to be both pieces. Type 1 error is rejecting the null when the null is true. So if power, type 1, type 2 error, if they don't all have 2 pieces, then you have not identified them correctly. And then correlation and regression. Remember, there's a lot of things you can say and a lot of things you can't say and a lot of maybes, right? So just make sure you focus back in on that. A couple of things we already talked about. We only interpret the y-intercept when it's reasonable that x can be 0. Always interpret the slope. Make sure you know your 3 criteria for when we use the regression equation to predict, right? Number 1 is we need to make sure that the value of r is reasonably large. Number 2, we need to make sure that the picture looks reasonably good. And number 3, that we're not predicting really far outside of the possible values of x. So if x goes from 40 to 80, I can make a prediction for 35. I can make a prediction for 85. That's fine. That's not very far outside of where we have data. But if x goes from 40 to 80, I would not make a prediction for 120. That's way too far outside. I'm not going to give you a tweener case. I'm not going to give you something that's too confusing. If it's barely outside, you're fine. If it's really far outside, you're not fine, and that's extrapolating, and that's making a prediction for an x that we don't have data for, and we wouldn't want to do that. Remember, correlation does not imply causation, so when we think about what that means, right, we have 2 options. You either say A, if 2 variables are correlated, one potentially causes the other, or B, you have some cases where you can say, I know it doesn't cause it because I know there's a lurking variable. You can never say that because A and B are correlated, A causes B. We can never conclude. The only way to determine if one thing causes another is by a designed experiment, and that's not a correlation regression analysis. A designed experiment, something we covered way back in chapter 1, that's where we have a control group that exhibits all the same characteristics as the treatment group, and the only difference between them is the treatment that's applied, right? And that's the way we determine causality, not via correlation analysis, all right? So that's going over the review there. Just as a reminder, if you have any questions, shoot me an email, let me know, and best of luck studying for your final.